All right, starting 4.5, after learning all those exponent rules, after learning all the good stuff, all those properties, you may even want to have it in front of you, maybe. Something you can kind of see which one you need to go back to. Usually the questions here are, Mr. H, why did you do this right here? How did that become a 4? Or some questions like that, and we'll handle those as we go. But let's go for it. First of all, we're going to handle multiplication, then we're going to handle division. So really it's just those two concepts. Go ahead.
For the test, can we have 2 3x5 since it's 2 different chapters?
You can have front and back.
Oh. Okay.
Okay, let's go for it. So multiplying this right here, hopefully you printed out the matched problems. Raise your hand if you've printed out the matched problems for today.
I got 4.6 in that.
Oh, cool.
I
Okay.
thought we did 4.5, but I guess we didn't.
That's what I thought too.
So I don't have 4.5.
Sorry. Okay, I'll go a little slower. Just, you'll be writing a little faster, that's all.
Yeah.
Okay, so let's go for it here. We're going to multiplying polynomials really means the first part is really this called a monomial, just one term multiplying several terms. So this in this case it's a monomial multiplying a trinomial. And what we do, kind of like a distributive property, except you had to distribute to every single one of them here. And again, like we did before, we're going to have to multiply the coefficients first. So half of 10. I go with the 5, and then remember exponent rule says if I'm multiplying 2 exponents, all I got to do is, 2 numbers, all I got to do is add the exponents if it's the same base. How about c to the 4th? Next one, ooh, that's no fun. 3 does not divide 2. So let's leave it as 3 halves. And anybody c to the what? Cool, I go with 3, is that right? Because there's like a little 1 here that we don't see. We assume the 1 is here, so 2 plus 1 makes the 3. So just adding exponents here. And last one here, half of 2. 1. The only thing is you can't put a 1 if you like, but if you just have variables only coming in, so c squared is also going to multiply. So just c squared. If you have a little 1 right here, that's fine too. But normally we don't write 1s in front of our variables. Okay. Good. So distributive property. Technically that's what it is. If you have a monomial, a single term times multiple terms. Then the question comes up, what happens if you multiply multiple terms times multiple terms? Cool. Well, here's it's almost like a double distributive property. Sometimes we call it FOIL. So this little y here has to multiply times every single thing in the other parenthesis. And this little -1 has to multiply every single term in the other parenthesis here. So 2 times 2y. And what we do is we have this little acronym that we use. I think you guys heard it before, something called FOIL. So what we do is we multiply the first ones together. That's what FOIL stands for, first ones. Then O is the outside terms. Y times 3 is 3y. The I stands for the inside terms. Now we're working with the -1. -2i. And then the last terms is the L. So notice, but really I want you to understand that really every single term in one has to multiply every single term in the other. If you got that, you have the more generalized concept here. All right, now the question is, are any like terms to put together? Yeah, 3y minus 2y makes 1y, or just y. So yeah, you do have to simplify as much as you can, so the middle term really just becomes a plus y. Oh. And you have that. And that's one form. The other form that we sometimes use is something called the column method. That's what this is all about. Column method, multiplying this right here. Again, notice that it's the same exact problem from before. Cool. So here's the column method. We'll put the two, it doesn't matter which one goes on the top, which one goes on the bottom. but this should be somewhat familiar. Does that look like multiplication with numbers? Something maybe like this, like I don't know, 45 times like 17 or something like that, right? Kind of looks like that. And this follows the same process here. So -1 times 3 is -3. Then we go to the next step, which is this one here. 2y times -1, -2y. And once that is done, then we start going to the next level here, which is that y. So 3 times y. And we're going to write it underneath here. Some students put a little 0 here. That's fine too, like a placeholder, exactly what you would do with multiplication. And y times 2y makes 2y squared. Don't forget to put a little plus sign. If you're going to add stuff to the front of a positive number, you're going to have to put the little plus sign. Anyways, do we get the same thing here? Hey, sure did, right? Adding. So both ways work all the time. FOIL tends to be the more often used one, because then you have to rewrite the problem. But just sort of you see that you can do it both ways. And technically what we're just doing, we're just multiplying. We're doing this process of 45 times 17, except the process has changed because now we have variables. That's it. So we're just using this, doing pre-algebra but with variables. All right, so let's move on here. So any which way you want to do it. My preference is probably the FOIL method as well. So 1/2 t plus 1. Let's see, 4t minus 4. Multiplying those out. Again, first one's half of 4 is a 2. T times t is t squared. Multiplying the outside terms here. Half of -4 is a -2 with a t. One times 4t is a positive 4t. And how about at the end, how about a -4? And again, any like terms to add together again. Yeah, those middle terms again. So how about 2t squared? How about plus 2t minus 4? Alright, and the reason why we use FOIL, because many times we multiply 2 terms times 2 terms, or a binomial times a binomial. Where the whole term breaks down is when we multiply more than 2 terms at a time. Kim?
Okay. How did you get 2t squared from the half t times the 4t?
Awesome. These are the questions that, again, I'm expecting, because this is where the questions come from. So 1/2 t times the 4t, the first term that we do. So half of 4 is going to be a 2. And remember with the t's are multiplying together. There's like a little 1 here, a little 1 there, and add it to 2. Okay, so how about more than 2 terms? And again, the whole concept is each term in one multiplies every single term in the other. Absolutely, yep. It's x times everything else here. Then you go through it again, 2 times everything else.
Oh, okay.
And then gather together like terms afterwards.
Yeah.
Give you guys a little bit of time to start, if you're not done yet. Let's see, first line here through will be 4x cubed plus 2x squared plus 3x. Everybody good there so far?
Yeah.
Alright, multiplying the 2, probably easier here because you're just multiplying constants, so 8x squared plus 4x plus 6 at the end, and then have to still gather those like terms together here. No x cubed except for the front ones. I have 2x squared, look at that. 2x squared and then 8x squared, 10x squared. Awesome, there it is. The x's make a 7x plus 6, and there's my final answer. Raise your hand if you say so much easier than graphing, Mr. H. Oh, I love this chapter compared to graphing.
I think I like graphing better.
Okay, the other way. I mean, like graphing better. Sorry, you're the only one. Okay, so let's.
When you have squares, you don't add them. You just keep them on the right term.
Good. So whenever you multiply, that's the only time that you would count or add up the exponents. Whenever you add or subtract numbers or gather together like terms, probably a better way to say it, you don't touch the exponents at all. Because the like terms are determined by your exponents. Like x squared here, x squared, that tells you can put these guys together. But the way you put them together is by adding or subtracting just the coefficients.
So you multiply them, you add them.
Perfect, yep, Another way to see it, which may make sense here for you guys. With exponents, it's kind of weird how they are one level lower, and let me try to explain it this way here. Whenever you do exponents, I'll put exponents here. Exponents, whenever you're doing nothing with exponents here, you're adding and subtracting exponents here, and then you're multiplying and dividing them here. So whenever you take exponent of exponent like this, 4 to the 3rd power to the 5th power, notice right here you're doing an exponent problem, right? But really what you're doing is you're multiplying the exponents. Does that make sense? It's one level, it always goes one level lower on the please excuse my dear Aunt Sally. If that sort of made sense to you. If it did, that's cool. Okay, let's go for it here. How about multiple variables at the same time? I'll put a k and a j at the same time. How about a v and a y? How's that going to work? Distributing the j to the 3rd, that would give me, and again, it doesn't matter which order the variables go, but traditionally, normally, you always write them in alphabetical order, because then it's sort of most like standardized across everything here. So between k and a j, C, D, E, F, G, H, I, J, K. Yep, nope, it's backwards, but that's okay. Okay, multiplying over here gives you a negative k. Now this would be j to the 4th. Everybody agreed there? And then multiplying all the way to the end, j to the 3rd. Notice they are not like terms, right? None of them have same exact variables, same exact exponents. All right, B, all yours. Foil it all out. Just kind of be careful with different variables at the same time. Alright, so how about y squared? That's what I got here. Vy for the middle, and then I got a minus Vy minus 2v squared. Also helps to keep them in alphabetical order, or at least a certain way to do it, because then you can see your like terms right away, which is the middle terms there. So positive Vy minus 2Vy makes a negative Vy, so rewriting it all over again, collecting all the like terms. jumping to C and D. How about 3 different variables? How about that? Alright, I'm going to try it as well here. Just look up when you are done. See if you agree with me. Alright, the variables don't have to be exactly in the same order as mine, but as long as you have all those terms and the variables there. And D, a little bit easier here. Let's see, x times x is x squared. X times z is xz. I'm going to subtract yz, or xy, sorry. And at the end, subtract a yz. Any like terms there? I don't think so, huh? None of them share the same exact variables there. Alright, 2 last problems here. Of course, they're word problems. So the length L of a rectangle is 5 more than the width, and we want to write an expression in terms of, for the area, just in terms of width only. Alright, since it's a geometry problem, I guess I should make a little rectangle then. Alright, rectangles have length and width. And so we don't know what the area is, but we want to create a formula that will give us area. Alright, we do have a relationship, is the length L, okay, of a rectangle is 5 means the equal sign right away. 5 more than. Oof, okay, if you guys remember this one. Remember more than, less than, those work backwards. So it's 5 over here at the end. 5 more than something, it's more than the width. And so we got it. There's the length is 5 more than the width. Got it. Okay, now let's write in terms of area here. Area is equal to, and the general geometry formula is just length times width. And the length, so we want the area in terms of just W. So that means we want to get rid of the L, somehow substitute it out. And yeah, we do have a way to do it because we know that L is the same thing as this. So let's bring this in here. That's going to be W plus 5, still multiplying this little W at the end. Cool, there it is. I got area just in terms of width only. So then here's my distributive property again here. So there's my formula. Kind of cool. I just created a formula where this sort of you've seen is if you sort of open up a window on a computer, or especially like a picture or something like that, there's going to be a relationship between the picture width and length. So if you want to keep it like a 4 to 6 scale or a 5 to 7 scale, and if you drag this out, these two have to be in the same ratio still, right? And so this formula kind of gives you, okay, this is the area if the ratio stays the same, what's going to happen. If it just sort of expands out bigger, it gives you that. All right, how about another one here? How about more of a business application here real quick. So electronic sales sells X CDs each day at a price of P dollars according to this expression. So normal buying of stuff says if I put a certain CD at a certain price, it's going to sell according to this right here. Now let's think of the formula just for a little bit. So that means if the price, let's say I set this at $1, P is 1. So that means it's kind of times 50, 300 to subtract 50, so that means I would sell about 250 CDs if the price is $1. Bump this up to $2. That's going to be 100. So that means 300. That means if I sell the CD at $2, I'm going to sell about only 200 pieces each day. So eventually, if you get up to $6, you're not selling anything at all. It's not worth it. Must be some horrible CD, I gotta say. But we'll go from there. Our revenue formula is this right here. Its revenue is always equal to the number that you sell and the price that you sell it at. Right? So it's not so much as how much things cost. It's really what's the volume in sales. That's what's really important. All right. I want to write a daily revenue formula, really just in terms of the price itself. So notice the X right over here. I can replace that with 300 minus 50p. So now I control not only just how many I'm going to sell, now I'm controlling by multiplying the p in. I get to plug in one formula as long as the relationship between the price and the amount sold is true. Now I got a relationship that gives me, I put in a price, I'll tell you how much I can make in that single day. Just sort of combining formulas together. Okay, good there. Again, application section of this stuff. Alright, that was 4.5, jumping to 4. Oh, sorry. Sometimes you can write it like this, sometimes you want to write it like this. I prefer writing the one with the highest exponent first, and then you sort of go down. This is called standard notation. We'll get to this when we get to chapter 5 for sure. We will want to write things in standard notation because we're going to learn how to factor stuff. Do you have to write it like this way? No, you don't. But come chapter 6, that'll be a good preference to write it that way. Alright, that's 4.5. Now jumping to 4.6. Alright, instead of giving you the practice problem or the match problem, let's look at just an example. Just real quick, right away. Alright, these guys are called special products. So remember we just figured out how to do FOIL? Well, FOIL is a pretty fast way of doing stuff, but we want to learn some other little ways here. And it only works for certain ones. Why do we want to learn this? Because in chapter 5, we're going to go backwards. And so by chapter 5, we do have to memorize. Well, it'll be good to memorize these formulas or these special forms we're going to use. Okay, so the first form, we're going to do it the long way, You don't really need to write it down if you don't want to, but at least pay attention to see what's going to happen here, because I will give you the formula in a little bit here. Okay, so find the square of 3x minus 2. So if that's the case, what we're trying to do is we're trying to find 3x minus 2 times another 3x minus 2. So this is the special form. Really, it's the fact that we're multiplying the same thing times itself. So instead of doing FOIL, the question is there a faster way to do this? That's the question. So let's go for it. Multiplying the first ones together, 3x times 3x is 9x squared. Multiplying the last ones together, 3x times negative 2, or the outside terms, it will be 6x. Inside terms, negative 6x. And that's what I want you guys to notice first. Look at this. Notice if you're going to multiply the same exact thing together, the outside term and the inside term will always multiply to give you the exact same thing. Alright, then at the end, negative 2 times negative 2 is a positive 4. Okay, so we gather like terms together. Negative 6x and another negative 6x makes negative 12x plus 4. So now let's sort of break it down. Let's see if we can actually just look at the problem only and see if we can come up with this answer right away without really writing anything down except for the answer. Okay, so looking at this problem, notice that 3x is going to multiply itself, right? So without writing anything down, can we get to 9x squared right away? Okay. The last term is also easy. A negative 2 times negative 2, since you're multiplying itself, everybody okay with the positive 4? Okay, so now let you draw it out real quick. So that's the squared part. The middle section, that's sometimes a little weird section here. Notice they're always going to double, right? Because you're always going to get the outside term and the inside term are going to be the same. So tell me if you guys agree with this. As that the middle term is really, we take this sign here as a sign here, and we're going to double whatever the product is of the two numbers. So it's going to be 3x times 2, which makes that 6x right here, and we're going to double it to give you that 12x. And then to how to get our sign is just going to stay the same. Okay, good there? Let's just practice on one. We're going to do it the long way, but we want to see this little pattern coming out from the long way here. So, hey. Sorry, class, messed up here real quick here. I wanted example 1. Let's do it the short way. Don't need to write things down, just kind of think with me, okay? Got this right here. We're going to take the 3x and we're going to square it. Minus 2 times the first term times the last term plus always. The reason why there's always a plus here is because what's negative times a negative? Positive. If this was a positive? Positive times a positive is, it's always going to be positive right there. Cool. Alright, so in your mind, could you go from here to here? So 3x squared gives a 9x squared. Minus, and then we're going to take the 3x and the 2, that's 6x. Double that gives you 12x. Plus, take the 2, square that, and you're done. I think I like that a little faster. Okay, what's the rule? I already gave you the rule, it's right here. It's x plus y to the second power. And the stuff in blue you want to write down again. 3x5 card would be a good thing here. So x squared plus 2xy plus y squared. There's your little rule for. And there's just a whole bunch of examples right here. Yeah.
So what if it's cubed?
We'll get there. Yeah, that's gonna be a little different. Alright, so this one right here, x plus y to the second is square the first term, twice the products, square the last term. Done. Alright, so now number 1, sorry, x minus 5. Again, we'll try to do it the quick way here. So it's x minus 5 to the second. Can you write down the answer right away? take the first term, you square it. The minus sign comes down. X times 5 is 5x, but the middle is going to double, so how about a 10x? Plus sign, square the 5, and gets us 25. Love it. I love it if I can go from problem to answer and be done. All right, two a little bit more complicated. Let's see. Kind of throwing some weird stuff at you just for a little bit, just to make sure we got it. I think the way they did this here, because sometimes you do want to write out the formula when it gets a little bit too complicated. So see if you can do it in your head, and if you can't, then do it by the formula. Alright, so y squared being squared, and again, I'm going to write out the formula because if I do it in my head, you're not going to see anything. Plus sign this time. We're going to take 2 times the first term times the last term, plus the last term being squared. Good? Got some exponent rules here though, right? Because you already have you're squaring something, and that square is already a square itself. So that's why you have that y to the second to the second. So, final answer, how about y to the 4th plus 2xy squared plus x squared. And again, notice the variables are in alphabetical order, right? I put the x first and the y. Don't have to do it that way. If you wrote down 2y squared x, that's fine too. Alright, and B, all yours. Can you go from beginning to end? Again, write down the formula if you need to, and if you don't, just write down the answer. Alright, final answer here, y to the 4th, let's see, minus 2xy squared plus x squared.
In the test, will be the answer be alphabetical order though? So it says that we do know.
Yeah. Question is, should we put the variables in alphabetical order? On the test, will it be so? Yes, it will. And we might as well get in the habit because in chapter 5 we're going to do it anyways. Alright, also I want you guys to notice something here. Notice these are exactly the same. The problems are exactly the same except for a sign change in the middle. So now the question of the answer. What's the only difference between the answers?
Negative 2x.
Yeah, it's just that middle one, right? It's not the end one, it's just that little middle. It's the positive when it's positive and negative when it's negative. Good there. So the sign change only happens for that middle term there. Okay, we're going to do some practice problems here. Again, see if you can go directly from problem to answer right away. Done. So number 3. I'm going to write down the formula each time. And if you need to write down the formula, write it down. But if you, or plug into the formula, I guess I should say. Alright, 2x minus 1 squared. I got a 2x that's going to square. Again, the minus sign, 2, and then first term and the last term plus the last term being squared. So final answer, hopefully you guys got this here, 4x squared minus 4x plus 1 should be the answer. Again, hopefully do it in your head. And again, show of hands, how many are doing it in their heads without writing anything down? 1, 2, 3, 4. Okay. And that means the rest of you guys are writing down the formula. That's fine too.
That formula is kind of throwing me off. Is there like a way, would I just put 2x minus 1 times 2x minus 1? Can I do it that way?
You can if you like, yeah.
Okay, backs out of it, please, it's
You're going to FOIL it out, but yeah, it's fine. And again, coming up on the next chapter, we're going to know the formula, but we have to know it going backwards. That would be a little different. Okay, number 4, all yours. Alright, I started as well here. Hopefully you guys are almost done here. So squaring the first term, double the product of the two terms, and square the last term, eventually 9a squared plus 12ab plus 4b squared. Any questions on that? Because I got a few people here looking up at me and at the board and erasing and doing the other stuff.
Works with the binomials, that's the one I did.
Perfect, yeah. Only works with binomials and only works if you have it to the second power, not third or fourth or anything else, when you're just squaring them. Alright, number 5. Alright, let's go for it. Squaring the 5x, again, product, doubling the product and squaring the last term. And hopefully that is what you guys got. A couple of people changing their answers, that's okay too.
Okay, so I got that answer right, but the last one I got wrong.
All yours for number 6. Alright, the funny part here is that the x and y are both on the same side. Then you got the 4 all the way at the end. So you got xy, so you're multiplying an xy times another xy. So each of them have an increase of 1 on the exponent. So you have x squared, y squared, hopefully. That's the little tricky part there. If you got that, I think you got the rest. Good? Yeah. Because you're squaring this one, so the 2 goes to the x, the 2 also goes to the y. Multiplying this gives you negative 8x y, and then how about a 16 at the end there? Okay, so that's one rule that we'll learn. The other rule is this one right here. I'll give you the rule and then we'll just do an example here. So how about if you're multiplying the exact same numbers except the sign in the middle has been changed? So one's a negative, one's a positive, or one's a positive, one's a negative. So let's see what happens. We'll do it the long way.
Should we write this down?
The rule, yes. Write down the rule, not necessarily the example here. Alright, and it was, again, we're just sort of recognizing the pattern. If the pattern fits, then we're going to give the answer here. So let's look at an example here. How about x minus 7 times another x plus 7? I'm going to do it the long way, see what happens, and then we'll shorten it up. So, FOIL method says x times x is x squared. X times 7, multiply these guys together gives you that 7x. First, outside, inside is the negative 7 times x, gives you negative 7x. And then negative 7 times the positive, how about negative 49? Alright, last time the middles doubled. This time, what do they do? Cancel each other out. That's it. They're gone. So really the answer is just x squared minus 49. So now the question, again, for the people that like to use FOIL is no need to do all of FOIL. All we got to do is just really the first term, last term, and done, right? So it's sort of, you don't have to do the middle term, the middle terms for that. Again, just trying to simplify FOIL. So these ones probably going to be the easiest ones here. Okay, so number 7 on our match problems here, all yours there. Should be pretty easy. First and last, and you're done. So x squared minus 16, we good there? And of course they do get complicated here, so jump to number 8. Again, shouldn't take you that long here. We're going to square first term, subtract 1, done. Number 9, all yours. And hopefully go straight to answer for these. So squaring ax times another ax, a squared x squared, everybody good there? Because now there's a to the 1, another a to the 1, you do have to add the exponents to give you that 2. And at the end, how about a subtract 4? Cool. Number 10. Should be the easy one here. X squared minus y squared, and done. So how about 4t squared minus s squared? Everybody good there? Again, slow me down if you need to here, but there's number 12. About 9v squared minus 49 for 12. Cool. All right, and number 13, again, how about all variables? Can you handle just the variables? All right, a squared x squared minus b squared y squared. Everybody good there? All right, pretty easy. All right, I'll give you a more difficult one, that's fine. All right, how about all variables and fractions? Or all variables with fractions, I guess.
We just do the reciprocal, right?
I don't know.
1 times a over 1.
No, no need to do reciprocal. Just you got to multiply whatever it says to multiply. Stretch your brain a little bit here.
Do you look at it the same as like a number and forget the a is the one bottom?
You could think of the 1 over a as almost like a little number, yeah. So you're multiplying almost like a 1/2 times a half, or what's a third times a third gonna sort of give you. Again, just going a little more abstract here.
Oh, okay.
And the x's are there, so x times x will just give you the x squared.
So the first one's 1/8 x squared. Right?
Not 1/8 though. Let's go for it. Let's go for it. So multiplying 1 over ax times 1 over ax. So 1 times 1
1.
is 1. I think I'll even do it off to the side here. Multiplying that together. So 1 times 1 is 1. What's a times a? A squared, because you just add the x's together, and then x times x, x squared. On the other side, you got a minus sign here, of course, but hopefully you can do this now here. 1 times 1 is 1. If you needed to just see it off to the side here, you got the b squared and the y squared now. Ah, most of you guys waited for me to do that problem. I see. No, okay. All right, this is this is okay. This would be a correct answer, no problem to write it like this. Sometimes we want a different form, and you can actually remember this x squared is really x squared over 1, right? You can always change it to a fraction. So technically, this x squared is on top. So you can write it like this as well: x squared over a squared minus y squared over b squared. That is perfectly fine as well. That formula now is something called formula for a hyperbola. It's how comets, how they fly, is really by this little formula right here. It's a kind of fun little formula. Okay, and of course we've got to get that word problem in as the last one. So write an expression for the sums of the squares of 4 consecutive even integers, then simplify. All right, so let's talk about consecutive even integers. Have we talked about consecutive even integers before?
Yes.
Okay. So let's quick reminder here. If you got this already, then don't need to write it down, but if you want to write it down. So let me start writing down consecutive even integers like this. 10, and then it goes on forever, right? You could also start at the negatives too. You could start off with negative 84 if you like, right? Okay, but if the first one, we don't start off and we don't know what it is, what do we need to add to that first one to get to the next even integer? A 2, so it would be x plus 2, whatever that x is, right? We could have started x as 22, so the next one would be 24. All right, what should we add over here to get to the third consecutive integer? So So if you start off with x, that means if you go the correlation between 2 and 4 is you're adding 2. The correlation from 2 to 6 is now you're adding 4 more each time. Good there? And then go from 2 all the way to 8. Now you're going to be adding 6. And then going from 2 all the way to 10. You'll be adding 8, and then you're going to go so on and so forth. What we need is we need the first 4. And we need to sum the squares of the first. Whew, that's kind of weird. Let's see what that looks like. So sum, I'm going to be adding, and I'm going to be adding the squares of the first 4 consecutive integers. So I take these 4 right here, take the first one, and I square it. I'm going to add it to the next one, and I square it. The third consecutive integer, and I square it, and the fourth consecutive integer, and I'm going to square that one. And again, I want to get a formula that allows me to see all that. Okay, you can do FOIL, but this is a process in which you really want to see if you can go by formula. I'll do the first one. X plus 2. Remember that? We square the first term. We take the x and the 2, multiply together, so the products, 2 times x, and double it, so 4x. Take the 2, square it itself. Everybody good there? Plus, and you guys get to do this one here, so x plus 4 squared. So how about x squared plus 8x plus 16? Does that work? Does that make sense there? Square the first term. The x, 4 and the x multiplied together would be 4x, and then double it. And then take the 4 and square it. So how about this one here? That's going to be x squared. Let's see, x times 6 is 6x. Times 2 makes 12x, and then 6 times 6 is 36. Alright, now let's add everything, all the like terms together. I got x squared, another x squared, another x squared, another x squared. So granted, I got 4x squareds. 4x plus 8x is 12x, and 12x plus 12x is 24x. And let's see, 4 plus 6, that's 20. 20 plus 36 is 56. Are we good there? And again, some practice with these things here. Okay, that was multiplication. Multiplication with variables. So now we're going to turn around and we're going to start doing division here. 4.7 is the easy one. It's division by a monomial, so a single term on the bottom. And we'll jam through this one. 4.8, that's when it gets a little bit more heavier. Alright, so as way of example, how do we multiply a polynomial by a monomial? Monomial just means we have a single term on the bottom, that's it. Well, this is easy then. If you have a single number or single term on the bottom of a fraction bar, what we're allowed to do, we're allowed to split it into 2 different fractions. And once you split it, then what we do is we do each individual fractions by itself and we're done. So again, the 10x cubed minus 15x squared, break it down with the 5x under each one, and then these are the rules that we learned in 4.1, 4.2. Divide the numbers, subtract exponents, divide numbers, subtract exponents. This is the easy section. Let's go for it here. Of course, I'm going to make it a little bit more complicated than just the example problem. So let's divide 36a to the 4th minus 48a squared. All that divided by 3a. So it would technically look like this at first. Would split off the 3a for each one of those. So 36a to the 4th, a3, or 3a on the bottom. reducing the 3 and the 36 to 12, and 16 for the 3 and the 48. And how about a final answer of 12, a to the third minus 16. Everybody go with just a, right? Subtracting the exponents on the a values. Alright, and the rest of them work exactly the same way. You might see maybe 2 variables or 3 variables at the same time, but the process is exactly the same. Any questions on 1? Alright, let's go for it. 2 is very similar to 1. And this one you may be able to do even in your head without writing anything down, because 25 divided by 5 would just be a 5. We know that to be sure. 5x, the x squared stays the same because there's nothing to divide the x by, right? There's no x's here. And then 5 goes into 50 10 times and done. Cool. Number 3 has 2 variables, the d and the x. So can you solve that one? I'll give you a hint. D to the 6x squared, we're going to divide that one by dx. 2dx divided by dx. Remember, if there's no exponent showing, there is still a little 1 there that we don't see. So d to the 6, d to the 1. So got to handle the d's first here. So that means d to the 5 power. Everybody good there? So then there's like a little 1 right here that we don't write down. But x squared here, x to the 1, 2 minus 1 is just a 1, so just an x by itself. Since there's no variable here, so no coefficient here to divide the 2 just stays. And whenever you have the same exact variable, same exact exponent, that means they're just going to cancel themselves out. So the d's cancel, the x's cancel, there's your final answer. Alright, number 4, all yours here. Try by yourself. Again, the 7 t's dividing each of those pieces. Alright. Dividing each of these by 7t gives you 7t for the first one to the 6th minus 3t. Everybody good there? Cool. Good. Getting better. This is good. Alright. How about, again, 2 variables at the same time? Let's try that. I'm going to start it off here. So this is divided by uv. So again, u to the 5th, u to the 1 makes u to the 4th. V's are the same exact variables, same exact exponents, so those canceled, they're gone. Minus sign this time, the u have the same exact exponent, so those are gone, and 3 minus 1 is a 2. So I let v to the 2nd. Alright, any questions on those? Cool. Alright, and number 6. Whew. Looks scary at first, but I'll let you guys try it first. Alright, I'm going to start it as well here. So under each of these, there's a 9a squared b squared. And then tackling one at a time here, 9 goes into 45 5 times. The a's canceled because they're both a to the 2nd, and then it's going to be to the 6th. 9 goes into 27 3 times. So let's see what's going to have. 6 minus 2 for the a is going to be a to the 4th. 3 minus 2 would make just a b by itself, or b to the 1, but preferably we would keep the 1 out of there. And 9 divided by 9, those will cancel. But a to the 3rd subtract, or 3 subtract 2 is just going to be a 1, and 5 subtract 2 is going to be a 3.
If we lower the number 1, it's still count, right?
Yep, so if you wrote down 1 in front of the a, b to the 3rd, that's okay. If you wrote down 1 for each of the variables, like each of the exponents for, if you wrote a 1 here for the b, 1 for the a, that's still just fine. Alright, show of hands, how many got number 6 correct before I gave it? Ooh, awesome, almost everybody. Okay, so if you think that's easy, let's move on to 4.8. Okay, so far we've been dividing by a single number, like 7t. That's fine. Or 9a squared b squared. That's fine. But the problem comes in is what happens if we try to divide a polynomial by another polynomial? Sometimes 2 terms, sometimes 3 terms, so this gets a little more complicated. But again, we're just doing division. And so if you give a pre-algebra sort of perspective on this, remember how we did multiplication? Well, this is technically, in a sense, long division. That's what we're going to be doing right now. So example number 1 from the textbook itself. Let me do that here. So 27, just for fun here. You guys don't need to do it, but let's see what's happening here. 27 goes into 39, is that right? Or first of all, we say 27 goes into 3, and it doesn't because 3 is too small. 27 goes into 39. That's going to go 1 time. And then what we do is we take this 1 and we multiply it times 27, right? It's the multiplier here. And then all of a sudden, out of nowhere, we start subtracting. Totally confused me. I still remember 3rd grade. Teacher put a minus sign there. I was confused for like 2 months. Why? Why you put a minus sign? Anyways, 9 minus 7 is a 2. 3 minus. And then the other part confused me. That's a 12. And then all of a sudden, it becomes a 126. 3rd grade was just not a good year for me. Okay, but the whole process then, once this is done, the process starts all over again. Is that right? And we do the same thing here. 27 goes in 126. How many times? It's 4. Then instead of multiplying by 14, we only multiply by this little 4 here, right? It's going to be 4 times the 127. Turns out to be 108. We subtract again. This time got to borrow, so that becomes 16 minus 8 is 8. 18 now, and then the 2 comes down. 27 goes into 182 6 times. And then we subtract again, leaving us with 20. Do you guys remember, let's see, 3rd grade. Remember writing down 146, and then remember putting a little R, 20 for remainder? I remember that. There's a capital R for sum. And then I finally figured it out. 4th grade, I was like, yes, I got this stuff now. So 4th grade, instead of writing R1 or R for the remainder, remember your teacher said, no, what we're going to do is we're going to write it as a fraction, because you guys know fractions now, right? So it's 146 and 20 over 27. Like, oh, this is so cool, you know? Then you bug all the third graders saying, no, you got it all correct. You got it all wrong. You're supposed to write it like this, and get them all confused. That was fun, too. Okay, but tell me if you guys agree. 146 and 20/27. Is this the same answer? Can I write the answer like this as well? Will this be still okay? Looks funny. Was it still okay? Yeah, I'm writing it just in terms of individualized units, right? There's 1 hundredths, and there's 4 tenths, and there's 6 units, and then there's 20 remainders. Okay. We're in algebra now. We're going to do the same exact process with variables. The process is still the same. It looks weird because there's variables in it, but we're still literally just doing long division just with variables. So before we get there, number 1, I'll let you guys try this by yourself just to make sure we're reminded of long division. More than half are done here. Wait just a little bit. This one divided evenly, is that right? Cool. Alright, so 36 does not go into 34. So 36 has to go into 342 9 times. We get that, we subtract. So got to borrow again here. So 12 minus, that's an 8. That's a 1. Bring down the 0, and then 36 goes into 880 exactly 5 times. Perfect. And we get ourselves a 0. Let's see, should I show it? I think I should here. Did you guys ever, this is called long division, right? So if there's long division, there should be also short division, is that right? So how about if I show you guys short division real quick here? And I'm again just making up stuff in my brain here. I don't know. There you go, that's fine. Okay, short division, how do you do this here? And usually works with individual numbers. Sometimes you could do it with 2-digit numbers, but it sort of works like this here. So 8 goes into 45. How many times? 5. What we do is we cross this off and we'll put a little 5 here. There's your short division. Right, because this is the leftovers if you subtract from 45, right? So now you think of 8 goes into 56. 7 times. This crosses off completely. And since there's nothing to carry over, then there's just nothing. So 8 goes into 7 0 times. This crosses out, and you got yourself a 78. And 8 goes into 78 9 times. That's 72, is that right? With 6 remaining, so it becomes 6 over 8, which reduces down to... Cool, we're good there? So that's short division. This is long division because you write down each individual piece.
And you can pretty much do that with any number?
It works best for like 1-digit numbers.
Right.
but 2-digit numbers, this one probably a little more difficult to see how it's going to work. That's why I didn't do it on this one. But that's what short division is. Not even going to charge you for it. It's a freebie of the course, okay? Okay, what's not going to be so fun is when we get to this right here. Okay, let's do example problem first, because I think it'll help us to get to the practice problem, because I don't want to just sort of waste it, the practice problem or the match problems. That's easy. So I'm going to do the example problem. If you want to do it with me, if you just want to sort of look, that's fine too. All right, how do we do this here? So we got, notice we're dividing by 2 terms now, right? You got x and the 3. That we're dividing x and the -3. So can't just wrap it up under, we can't just do this. We can't divide it out and put it underneath each of those pieces anymore. And that's the difference between 4-7 and 4-8. You got 2 terms here. All right, in light of that, let's go for it here. Let's put it into a long division sort of setup here. X minus 3 goes in front. And then we have the top here, x squared minus 5x plus 8. Okay, some rules here. Ready? This has to be going down in standard form, which means the highest degree on the x and then goes lower all the way to your constant term if you have one. So this is probably easier seen here. So x to the second has to go first, then x to the 1 power, and then the one that's the constant. So always have to go down in order on each of these. Second is you can't have any degrees missing. So notice it goes from x to the second, then it goes to the 1, right, and then to the 0. If the x was missing, we'll fill it in a little bit later. I'll show you how to fill it in. But you have to have each of the degrees represented. Mostly it's really just to put into columns. That's what we need them for. Or else we get crunched for space. Okay, next. We look at just the we call them the leading terms, just the numbers in front. That's all we care about. This x here and this x squared. Good. We normally do that over here too. Let me go back real quick here. Right, we did not look at 3,420. When we did the first one, we only looked at 342. We cut off the 0 for a little while. We only looked at the beginning portion. That's exactly what we do here. Okay, so how many times does x go into x squared? Goes x times. Now our column right here, notice our column is for the x. This is, we're going to use that as well. This is going to be our x column. So just like long division, we're going to take this x times x. It better be x squared, because that's exactly what we were trying to get in the first place, right? Then what's x times -3? -3x. All right, now the question is, what's that weird thing that got me confused in 3rd grade? We are going to subtract this thing out. Now, you know I hate subtraction, right? So I don't like to subtract, especially this right here. -5 subtract a -3. What is that can even be? Okay. I got a -8x for a possible answer. Okay. Which one do you guys want to do, subtraction or addition? You want to subtract?
Yeah.
Go for it. Okay, I'm going to add. See if we get the same answer. Yes. Here's what we're going to do. We're going to take this subtraction symbol and we're going to change it to addition. The reason why is because it's a lot harder to see subtraction than it is addition. So all we got to do real quick here is to change all the signs here. So negative for the x squared. This becomes a positive. So now it's a lot easier to sort of see what this answer is going to be. -2. So the x squareds have to disappear because that's the design. -5 and a +3 make a -2x. We'll bring down the number at the end. Okay, do you have to always change it to addition? No. If you can simplify and subtract easy, if it was a +5 here or a +3, it would have been worked. If it works out easy to subtract, subtract. If it works out easy to add, I would add. Okay. Whole process starts all over again. What number do you multiply x to give you a -2x? -2, right? The x is already here. The multiplier would be the -2, so we're going to put the -2 on top of here, underneath our column for our constant terms. All right, negative 2 times x. Better be negative 2x, because that's exactly what I was looking for. Negative 2 times negative 3.
6.
Positive 6. And we subtract. Now in this case, these are going to cancel, right? It better cancel. So 8 subtract 6, can you do that? Yeah. In this case, I probably wouldn't change it. I'll just write down a 2 down there, right? Because in that point I can subtract really easily. Okay, if you didn't want to change it, if you're just sort of one of those types that always want to do the same thing all the time, it'll sort of look like this. Notice these guys are opposites now, so they will cancel. 8 and a negative 6 make a 2. Okay, but 2 is the leftover piece though, right? There's a minus 2, that's part of our quotient here. So how do we write this all together? We're going to write it as sophisticated 4th graders, okay? We're going to write it as a fraction, not the r stuff. So we're going to say x minus 2, that's this part, top part over here. How do we include the fraction? We're going to say this plus 2 over what we were dividing by in the first place. Okay, good there. Real quick here, anybody want me to run it through again just to sort of see the process? Okay, let me just show you the process here because it just kind of helps to sort of stick it in our minds here. I'll go a little faster, but you're not writing anything down, so that's a good thing. X minus 3 goes down here. This one has to come down decreasing powers of x and every single term represented. So x to the second, degree 2, degree 1, degree 0. And these are going to be our columns now. So always look at the leading terms here. So x times what gives you x squared? It'll be x, so x goes on top for the column for x. So x times x is x squared. X times negative 3 is a negative 3x or a minus 3x. And we start subtracting. Sometimes subtracting is not so cool, so we change to addition and take all the opposites of all the signs here. Cancels. That's what we planned. Combine down and then write down the next term. Do the whole process all over again. X times what gives you negative 2x is a negative 2. This is, notice this is your constant column. No x's here whatsoever. But negative 2 times x is negative 2x. Negative 2 times negative 3 is a positive 6. And again, we just subtract or add the opposite. And we get ourselves an answer. Again, the quotient is listed by itself. Adding the remainder afterwards. Cool. All right, all yours for this one. So from beginning to end, all yours. All right, let's go for it here. So a plus 4. All right, here we go. 2a squared goes first, then the 5a goes next, then the minus 12 at the end. And so what number times a gives you 2a to the second? 2a, and we're going to write it underneath the a column. So 2a times a gives you 2a to the second. 2a times 4 gives you 8a. Good there? So far, so good. And then what we do, we subtract, aka adding the opposite. Okay, first term's gone. Negative 5 and a negative 8. Negative 13a. Hopefully you guys got that. Let's see if anybody's erasing right now. Okay, everybody good with the negative 13a? See, those subtraction addition stuff, man, not good. Mess people up. Alright, drop down the negative 12, and the whole process starts all over again. A times what gives you negative 13a? Of course, it's going to be negative 13. And negative 13 times a is a negative 13a. Negative 13 times 4, ooh, that's no fun. I got a negative 52. Alright, and we subtract, or how about just add the opposite? Alright, final answer, or remainders of 40. Can't go beyond that now. And final answer, 2a minus 13 plus 40 over what we were dividing by in the first place, a plus 4. All right, how many got that one correct before I gave the answer? Out of curiosity. 1, 2, 3. Okay. We'll practice with it. It usually takes like 2 or 3 until you get the hang of it, Kelly.
Can we simplify the 40 and 4?
Yeah, question, can we simplify this to? You cannot. And the reason for it is because, see this little variable a influences that 4 to something. So let me say this here. How about this? How about if a was a 3? Let's say a is a 3. In that case, you get yourself a 7. Because a plus 4 then would be 7. So there's nothing in common that they always have in common. Now, just out of, I'll stop there. Okay. Let me decide here real quickly here. Should we look at another example problem? Let's look at the example problem first here. Again, trying it with me if you like. This is an example from the textbook here. But just to sort of get us some extra time, just to sort of practice it. Alright, what's the difference between this one? The one that we did before is now you have a 2 in front of the x. So you have to think about the number and the variable at the same time as you do these problems here. Alright, but 2x minus 5 on the outside, and then in order of degree. So 2x times what gives you 6x squared? Yeah, I need a 3 and the x. I'm going to write it underneath or above the x column. So 3x times 2x is 6x squared as needed. And then 3x times a negative 5 makes negative 15. Alright, subtracting. And again, got the little weird negatives and all that good stuff, so I'm going to be adding the opposite. Makes it a little easier to look at.
So how do you know when to do that?
If, yeah, the question is when do you know to add the opposite or not? I would sort of take a look at this part right here. If I could do it quickly in my head, like 8 minus 6, I would do it. But if it's a negative 11 and negative 15 and I'm subtracting over here, might as well just change it to addition. Okay, so negative 11 positive 15 makes 4x. That's easily seen now. Bring down the rest of the problem. Alright, 2x times what gives you 4x? 2. So when you put up 2, don't forget to put a little plus sign right here, because you have a positive number, you're still adding to the 3x that's already there. So 2 times 2x is 4x. 2 times negative 5 is a negative 10. Subtract. Or add the opposite. Dun dun. So negative 14 and a positive 10?
Negative 4.
Negative 4 is good. Alright, writing down the answer, and let me just check something just really quick. Okay, I want to see how they did that. Okay, so you're going to write it as 3x plus 2, and then plus negative 4 over 2x minus. That's the way the back of the book does it. All the other textbooks that I've seen of algebra, what they would do, they actually would do it like this. Same thing, pretty much, right? You put the negative, you're subtracting the remainder here as opposed to adding a -4 as the remainder. So same thing. Okay, I think we have time for the last two problems here now. So let's jump to change the variable to a b. That should be still fine. And again, give you guys maybe a 30-second head start. Alright, so let me start here. So b minus 9 on the outside, and again notice you gotta put them all in order, going from the highest degree to the lowest degree, and they are like that already, so that's good. So then let me just try it here. So what times b gives you b to the third, b to the second. So notice that's why we build these columns in, because when you get b squared, if you don't have a b squared in the problem, you still need that column for b squared. Okay, b squared times b is b to the third. B squared times a -9 is a minus 9b squared. Again, looking at what you've done, just to make sure, I get a positive b squared, or 1, if you like, 1b squared out of that, as you're adding a -8 and positive 9. Bringing down the next term. So b times what gives you b squared now? Just the good old b. Don't forget to put a plus sign in front of that b because you're still adding to the b squared. So b times b is b squared. B times a -9 is a -9b. Subtract, or rather add the opposite. Hey, again, get myself a 1b or a b minus 9. So then b times what gives you b? That's a 1, right? Because it's the same exact number. That's a 1. Don't forget you're technically just adding a 1 because you're trying to get the next column in. So 1 times b is b. 1 times -9 is -9. At this point, if you're subtracting the same number from itself, you should know that's just a 0 already, right? Because you're, but b minus b, kind of canceling. If you still want to just sort of change them, you know, the b's are opposites, the 9's are opposites, so you don't have any remainder this time, and that's okay. We had that in long division as well. So the final answer, b squared plus b plus 1. There it is, not writing down the remainder. Show of hands, how many got that one correct before I gave the answer? Whew, 2, 3, 4, 5. Okay. Getting there, getting there. Okay, and the last one, the toughie. If we got this one, we're doing good. Two variables. Okay, and this one we do have to decide which one's going to be our leading variable. Which one are we going to sort of concentrate on doing? And it's the one that's going to be set up so that you are going on decreasing powers of that variable. So in this case, I look at the, not all of them have, let's see, this one doesn't have an s there. And notice there's an s inside this one, s inside this one, then it goes s squared. So s doesn't look like a very good one to use. How about t to the fourth? And it goes down t to the third. We're missing t squared, but there's a t to the 1, and then there's no t's whatsoever. I like t as my leading term. Sort of progresses down. So I'm going to write it as t plus s in front. Ooh, which one was missing again? The t squared was missing. Okay, how do we include that? Ready? T to the fourth plus t to the third s. I'm going to have to include it right here. Okay, how do I add something without really adding anything at all?
0.
I add 0 t squared. So I'm putting in the t for my column, but with that little 0 in front, technically I'm not really changing up the problem at all. Alright, and here's the only thing I'm thinking about here. I probably will have an s in there somewhere because all these guys here have s's. So I assume since the s started here, it's going to go to here, minus t times s. There's another s over here, and eventually a s squared. So I kind of make it so that it sort of fits the pattern as I see them. Alright, all yours if you want to stay ahead of me. so let's go for it here. So t multiplying what to give you t to the fourth will be t to the third. T to the third times t is t to the fourth. T to the third times s will give you that t to the 3s. Good there. And we subtract. Ooh, this is kind of fun. T to the fourth will cancel. And these guys, we're subtracting the exact same thing, aren't we? So those are gone. We're left with nothing. Oh, that's weird. Okay, then we go to this one, but this one just has a 0 in front of it, so really technically this is nothing. We just use it as a placeholder already, right? So if that's the case, that means the next term really is this one all the way over here. So we're going to bring down a minus ts and a minus s squared. That's the next term really on the list. Alright, so go back over here. Let's ready to start over again here. So what multiplies t to give you a negative ts? Just s, huh? Okay, now here's my little problem. I don't have like an s by itself. I have a ts category. I don't have s. So I mean, we're sort of getting towards the end of the problem. And I'm just going to write the s maybe like all the way over here at the end, because I know this is going to be the last part anyways, because I already brought down the last term. So I'm missing the little s column. Okay, but negative s times t, negative ts. Negative s times s. Hey, I got the same exact thing, and I'm going to have to subtract those. Subtracting those out, and again, really don't even need to add in the opposite, because I know if I'm subtracting the same thing or something from itself, I know it's just going to go to 0. So how about t to the third minus s? Alright, good there. Alright, that will be the end of 4.8.